Good morning, class. We are talking today, continuing our lecture on the method of joints. So we have done lecture number 2. Today is lecture number 3, which is method of joints. We will definitely finish method of joints. We may get started on the method of sections. I'm not sure yet, so we'll see where we get. This is method of joints part 2. This is lecture number 3. Okay. So the first thing I would like to bring to your attention is here on our Moodle page. At the top of the Moodle page, I have put a button to submit late homework for partial credit. This is any homework throughout the course of the semester. This is open until after finals. So anything that you turn in late, you can always submit here. There will be a submit button for our first homework coming up sometime this week. I think the homework will be due probably not. The homework will not be due this week. The button will be available this week. So, and then it will have a due date and so forth. And if you submit through the homework number 1 button when it's put up, you'll get full credit. If you submit through late, you'll get partial credit, but the partial credit will be based on how late you actually submit, because it will have a timestamp on it. So if you submit a little late, you're not going to lose probably any credit. If you submit several days late, you'll lose some credit. Okay? So having said that, the first thing we're going to do is to continue and take a look at the method of joints, which is the handout from your page. And we've talked about tension, compression, and how to find, we know that if we're pushing on the joint, that the structural member is in compression, and if we are pulling on the joint, the structural member is in tension. So for example, if you look here at joint A, well, let's see, what do we have here? This is joint E, isn't it, right here? And so you can see that if you look at force in DE, which is this structural member, you look at the direction of the arrow, it's pushing on the joint, isn't it? So that means that it is in compression. If you look at force CE right here, that is, there's something incorrect here. Oh, they've drawn it incorrectly. Okay, I understand what's going on. See, if you look at these two, look at force, look at joint E. Okay, we have one structural member, DE, that is purely horizontal. So what that means is, in order to maintain static equilibrium, the vertical component of BE and the vertical component of EC are going to have to sum to 0. So the way that it's drawn here, they both seem to have negative vertical components, don't they? This is pointing downward and this is pointing downward. That means one of them is incorrect. And if we do the math on that, which I'm going to do for you in just a minute, but I just wanted to see if I could find an example of the math. BE, not yet. DE, okay. You'll see that what we end up with is something has the wrong direction, and that puts that component into tension. So we're going to go ahead and take a look at that in just a moment. Okay, so coming over here to the document camera, when we have a joint, this is just a really quick review, the summation of forces in the x direction into that joint have to be equal to 0. And also the summation of forces in the y direction into that joint have to be equal to 0. And that is true in order to maintain static equilibrium. In other words, if that is not true, something is going to move. So by virtue of the fact that the truss is not moving, we know it has to be true. Now, the other thing when we draw a truss and we talk about looking at a particular joint, if we say here at A, we have some sort of an external force, and then we have the forces in the structural members. When I draw this joint, if we call this A, we view those forces in the structural members just as forces. So in other words, the geometry of the forces is the same as the geometry of the truss. Now, when we talk about whether something is in tension or compression, like I said, if it's tension, it's pulling on the joint. And if it's compression, it's pushing on the joint. Always referencing from the joint itself. Okay? Now, what happens when we get up here? Well, if we look at this, if the force is going this way at this joint, it's pushing on the joint. It's also pushing on this joint. Okay? So in other words, when we do the analysis here, every force changes direction. We don't necessarily know the directions of these forces yet, but this force, in other words, if it was down and to the left here, it's up and to the right here. That's because, once again, that structural member has to be in static equilibrium. The overall force in that joint from an outside perspective is 0. So whether it's pushing or pulling on a joint is how you determine the direction. But when you go to the other end, to the other joint, it's going to change direction to maintain pushing or pulling. And if you think about it, if we did this, if we had this force looking here, if it was going downward, that would actually rupture that joint, wouldn't it? In other words, it's not really, so it's a little different perspective than when we're doing an external free body diagram. Okay? So you have to think about that as well. So these are sort of the elements that we need before we get into doing a problem. The only other thing a structural member can be is a 0 force member. So it can either have tension, compression, or 0. And having said that, I'm going to go down to the bottom of this handout. I'll put this up on our screen in just a moment. And I'm going to do a problem for you from the homework. And I really want you to ask any questions that you have along the way. Some of this is a review of statics, and some of it is new materials. So make sure that you let me know. But when it says, for example, here on problem 610, determine the force in each member of the truss shown by the method of joints, indicate whether each member is in tension or compression. All right, the first thing I'm going to do, I will put up the document camera in just a moment. But the first thing I'm going to do is to draw the truss. And after I do that, I'll discuss a little bit about how the analysis is going to work, and some of the things that we're bringing in from statics and some of the things that are new. All right, so I haven't drawn the external forces, but I'll do that in just a moment now that you have this available to you. Okay, so over here on the document cam, you'll see that I've drawn A, B, C, which is a triangle, so therefore it's a truss. Now, A, the way that this support is drawn, means that it is a fixed support, and it can draw, or it can bear a load in the y direction and a load in the x direction. So in other words, we're going to have a reaction in the y direction and a reaction in the x direction, possibly. Now this at C, yes, sir?
No, I just wondered what that shape was at C.
I'm sorry, what?
What that symbol was at C.
Yeah, that's what we're going for next. This is called a rolling support. And a rolling support means, like, you remember we were talking about the fact that on a bridge or a truss, one of the supports has to be moving because otherwise it could buckle the truss. That means that this in the y direction will only move. It doesn't bear a support, it doesn't bear a stress or a force. So that means that we're only going to be able to have a reaction at C in the x direction. In the direction of the roll, it's just going to move to prevent it from getting into a bind. So there is no reaction at C in the y direction. So when you do your first part of the analysis, that's something you want to keep in mind. You don't have an ability on a rolling support to bear a force in the direction that it rolls. All right, so then here at B, we're told that we have an 8 kilonewton force acting in the negative x direction and a 12 kilonewton force acting in the negative y direction. And it asks us for the force in each member. So we are looking for the force in AC, the force in AB, and the force in AB, AC, BC. Okay? And we want to know each of those if it's tension or compression. So we know magnitude, because these are in kilonewtons. We want to report in kilonewtons. And we want to know whether it's in tension or compression. Please excuse me. All right. So let's start. We're going to draw a little. So the first thing we're going to do is to draw a free body diagram of the entire structure. So this should be familiar from statics. What that means is we have a triangle and we draw the forces. We have a reaction at A in the y direction, a reaction at A in the x direction. We have a 12 kilonewton force at B, negative y, and an 8 kilonewton force at B in the negative x direction. And here at C, we only have a reaction at C in the x direction. So these are the external forces on our truss. Now, what I have done here, everything that I don't know, all of my unknowns, I've drawn as being positive, positive x and positive y. I don't know if that's true or not. But when I do my analysis, if it's not true, I will get a negative sign, and then I'll know that I reverse it. Okay? But I always do positive. If you're fairly confident that one or the other is positive or negative, you can draw it that way from the get-go. But if you're guessing, always guess positive, because then it's kind of like in the English language how double negative is a positive, like I don't got no whatever, I don't got no money means I have money, which I can't imagine anybody would really think that's what you meant, but there you go. It's kind of the same thing. If you have a double negative, that would mean it was a positive. So if you do it this way, when you do the math, a negative just means switch the direction, which is a little bit easier. Now, having said that, if I look at my external forces, these are both x forces, right? And this is an x force. I also see that I have a 12 kilonewton force negative in the y direction. This is the only force, the RAY is the only one that I was going to say contradicts it. I'm still thinking of English. That counteracts it. So if this is negative, this has to be positive, doesn't it? Okay, so I'm fairly confident that I have drawn that correctly. But to do the math, I say summation forces x equals 0 and summation forces y equals 0. And I draw them according to the signs on my free body diagram. Another thing I always say is once you draw the free body diagram, always make your math correspond to your free body diagram. There's a country western song where this guy says he's lying to his spouse, and he says, "That's my story, and I'm sticking to it." So it's kind of like this. Even if you're wrong, stick to your story until you change the diagram. Okay? So we're going to go ahead and take a look at our x forces. And I have an RC in the x direction. I have a negative 8 kilonewtons here at B. And I have a positive RAX. And I know that those three things have to sum to 0. And I cannot explicitly solve this, but I can see that RCX plus RAX, if I bring this over to the other side, has to equal 8 kilonewtons. Okay, so I can't solve for these explicitly, but I will fix that in just a moment because I do have a third equation of equilibrium. Now in the y direction, I only have two forces, RAY minus 12 kilonewtons equals 0. RAY then equals 12 kilonewtons. And the fact that this is positive tells me that I have chosen my sign correctly. So RAY is 12 kilonewtons. Okay? So now I have essentially one equation and two unknowns. Can't solve it. Not possible. So what do I have to do? I need another equation. The next equation of equilibrium is the summation of moments about any point if equilibrium is maintained. In other words, if it sits still, the moments about any point on this truss have to be equal to 0. Now, if you remember, a moment is a vector, and it is some r, or moment arm, crossed with some force. Okay, now this is from statics or physics once again. In this case, because everything is in the plane, or since we're talking about a plane truss, I don't have to worry about anything happening in the z direction. The moment itself is a z moment. In other words, the axis of rotation is z. However, if I just realize that my forces are either x or y, I can take a moment arm to be perpendicular to that, because it's also the magnitude times the sine at the angle in between them. Okay? And some of this is, like I said, a review. So we're doing a little bit of trig right now. Some of it may be coming up with cobwebs, but hopefully, maybe you've seen this before. But if not, we'll just start from here. All right. So since a moment always involves a moment arm, the best thing to do is to choose moments about some point that I will eliminate a couple of forces. And if I choose point A, RAX and RAY have no moment arm because they're through point A. So if I choose moments about point A, I'm just going to have to worry about the moments from these three, and they will equal sum up to 0. So for my moments, I'm going to say the summation of moments about point A is equal to 0. Now, once again, I always choose as a convention, and Beer and Johnson in your statics book, but it can be different. But I always choose as a convention that a counterclockwise moment is positive and a clockwise moment is negative. The reason is that corresponds to the right-hand rule in physics. So as long as we're working in a plane, we can just use that sign convention. So what I do is I pretend like there's a pin here, and then I look at this force and I say, if I were to put a pin here and pull on this force, what sort of a moment would it create? In other words, would it spin this counterclockwise or clockwise? Well, let's look at the 12 kilonewton force. If I had a pin here and I pull on the 12 kilonewton force, it's going to pull it clockwise, isn't it? Right? What about RCX, the way I have it drawn? Pin, pull, also clockwise, right? What about the 8 kilonewton force? Well, 8 kilonewton is collinear with point A, so it doesn't create a moment at all. In other words, there's no vertical separation. So for my moment equation, these two don't have a moment arm. This is collinear, so I only have two forces creating moments. All right, at this point I need to write down what my distances are, because those will be my moment arms, 1.5 meters, 1.5 meters. All right, so since this is a vertical force, I have, since it's clockwise, negative 12 kilonewtons times the distance between here and here, which is 1.5 meters. And I have this drawn as a negative, RCX. This is horizontal, so I need the vertical distance, 1.5 meters. Those things sum together equal 0. So if I bring this over to the other side, I get negative 12 kilonewtons times 1.5 meters, which is negative 18 kilonewton meters. Bring this over to the other side, equals RCX times 1.5 meters. And to finish that off, I would divide through by 1.5, and I get negative 12 kilonewtons, because I'm dividing meters by meters, equals RCX. Okay, that tells me that the magnitude of RCX is 12 kilonewtons, but what about the direction? I've drawn it incorrectly, haven't I? So in other words, this is going to be pushing the other way. So I change this, and I say RCX equals 12 kilonewtons, but it's going that way because of this negative sign. All right, well now I know what RCX is, so I can solve for RAX, can't I? So RCX is to the negative, it's negative 12 kilonewtons, plus RAX equals 8 kilonewtons. And if I solve for RAX, I bring that over, I actually get RAX equals positive 20 kilonewtons. So this is 20 kilonewtons. Okay, now I've done my free body analysis on the truss. Now think about this. If I'm pushing this way and pushing this way, it makes sense that RAX is going to have to be quite large, isn't it? In other words, that fixed support is the only place that I am bearing that load. That's it, right? Okay. All right, so let's continue our work. Now we know what the truss looks like. Now we're ready to dig into it to get method of joints. Now, the thing about methods of joints, the one thing that you need to know, you only have two equations of equilibrium. You only have summation forces x, summation forces y. After you get done with the free body analysis, there's no moment equation because everything's going through point A, so all the moments are 0. So there's no analysis to be done from that. All right, but let's draw each one of my joints here. This is A. I know that I have RAY, which is 12 kilonewtons. I have RAX, which is 20 kilonewtons. And then I have two forces from the structural members. This is AB, and this is AC. Now, we may be able to infer something. For example, if you look at these four forces, this and this are the only two that have vertical components, right? So if this one's up, what does this have to be? Has to be down, doesn't it? Because what else would counteract it in that sense? So then here and here, this one is going to the left, this one is going to the right. We really don't know if this is to the left or to the right. So I'm just going to draw it in the positive sense, and I may have to correct that. Okay, now let's take a look at B. We have a 12 kilonewton force going down, an 8 kilonewton force going over, and then we have a vertical force, which is BC, and we have a horizontal force, which is AB. All right, well, we kind of luck out here at joint B, because what do you see? This and this are purely horizontal. If this goes to the left, this has to go to the right. And just because the summation of forces in the x direction only has two parts, we have negative 8 kilonewtons plus AB equals 0, and we get that AB is equal to 8 kilonewtons. Okay, so we've solved that here, but that also means that AB is 8 kilonewtons here. But if it's pushing on the joint, it's not pulling on the joint here. It's also going to be pushing on the joint. But AB here is also 8 kilonewtons. But the sign is pushing on the joint. Same thing with BC, right? We have 12 kilonewtons pulling down. Summation force is y equals 0. So we get negative 12 kilonewtons. This one has to be going up. Plus BC equals 0. BC, therefore, equals 12 kilonewtons. And it's going to be pulling up. This is 12 kilonewtons. Okay. So the last force that we need to cope with is AC. And AC is at an angle. This is where we're going to have to use a little bit more trig. We know that this is 8. We know that this is 20. We know that this is 12. We could do this analysis from point C if we wanted to. It doesn't matter if we do point C or point A. It's going to come out to be the same answer, which is the beauty of doing engineering stuff. What we're doing is looking for the reaction at AC. It doesn't matter if we start at A or we start at C. So since we already have A drawn, let's just go ahead and do that. Summation forces X equals 0. We have 20 kilonewtons minus 8 kilonewtons. This force, the 12, does not have any X component, but AC does. AC has an X component. The way I have it drawn, the X component is negative, so I say minus AC in the X direction, and those three things together have to sum to 0. Now I'm going to have to do trig to find out what this X component is, and I can find it entirely just from the X direction. So I'm not really going to need this equation, but it's also true that the summation of forces in the y direction have to sum to 0. And this might be, it's the same, it doesn't matter, but let's go ahead and do this. This says 12 kilonewtons minus AC in the y direction equals 0. Okay, so if I want to just work, like I said, it really does not matter which way, but this would be 12 kilonewtons minus AC in the x direction equals 0. So I have two equations to choose from.
You can't quite see that.
Oh, you can't. How's that? Is that better? Thank you so much. Yeah, I kind of get into working it, and then I forget that, I have a limited field of vision here for you guys. Okay, so let's take a look at how we're going to resolve that. What is AC in the x direction? Well, this is what AC looks like. We're told that this distance is 1.5 meters. We're told that this distance is 1.5 meters. So what is this angle going to be? Can you guys see that from trig? If you have an opposite and adjacent side to an angle that are the same length, 45 degrees. Very good. So this angle at A is 45 degrees. Now, if you're not comfortable looking at that, you could say, okay, opposite over adjacent is tangent. So the tangent of the angle at A is opposite 1.5 meters over adjacent 1.5 meters, which is just 1. So then you could say the angle at A is the inverse tangent of 1, which is 45 degrees. Now, sometimes you'll need to use your calculator and do a trig function, maybe, because the angle might be different than 45 or 30 or whatever. It may be an odd angle, and you'll have to do that. But the process is the same. All right. So what does that mean? Well, that means that if we look at this, for example, 12 kilonewtons is equal to AC in the y direction. Okay. Well, if you look at resolving this force, if this is AC, if this is AC in the y direction, and this is AC in the x direction, you can see that this is the hypotenuse of the triangle. This is the opposite hypotenuse is the sine, right, of that angle. So the sine of the angle at A. So if I'm looking for the opposite, which is ACY, probably can't see this again. There you go. Over AC, the entire force is equal to the sine of the angle at A. Or we could say that, I'm going to draw this right up here, sorry, to make a little jog. AC in the y direction, or the component of AC in the y direction, is then equal to the entire force AC times the sine of the angle at A, which is 45 degrees. And I can plug that in right here. So I can say 12 kilonewtons is equal to the magnitude of the force in AC times the sine of 45 degrees. Or the force in AC is equal to 12 kilonewtons divided by the sine of 45 degrees. Right? And we should all know what the sine of 45 degrees, 0.707, I think. Sine of 45 degrees is 0.707. So that means 12 kilonewtons divided by 0.707 is equal to the force in AC. And 12 divided by 0.707 is equal to 16.97. So let's just say very close to 17 kilonewtons. It's 16.97, but I rounded to 0.707, and as you know, those are all irrational numbers. Okay? So, let's go back to what I needed for answers. I needed AC, AB, and BC. So I know that the magnitude of AC is 17 kilonewtons. The magnitude of AB is 8 kilonewtons. And the magnitude of BC is 12 kilonewtons. And now I need to decide if those are in tension or in compression. So to do that, I go back to the joint, and I decide, are we pulling and pushing? AB. Sorry, yeah?
Is it just observational for the TNP?
Sorry?
Is it observational?
Oh, right. We're going to look for the question, is it pulling or pushing on the joint? Yeah, absolutely. Absolutely observational. No more math. Good question. Okay, so what's AB doing? Is it pulling or pushing? Pushing, yeah? So that's in compression. AB, compression. BC, pulling or pushing? Pulling, so that's tension. And now let's look at AC. Here's AC, pushing, compression. Okay. And this is the set of answers that you would have as an answer to that problem. Right. So do you guys have any questions yet? You haven't done one yet, but you have an example now. So, all right. So what I would like you to do in the next little bit, get together in a group or a couple of groups, however you see it, and work through problem 611. Okay? It's the same process, but you'll have to go through, do a free body diagram. B is a rolling support, so it's not going to bear, in this case, it's not going to bear a force in the x direction. B is only going to be able to bear a y directional force. At A, you're going to have a reaction at A and the y and the reaction at A and the x. So do a free body diagram of this truss. You'll also notice that the angle is not 45 degrees here because it's a 3-4-5 triangle. Okay? So there's a few differences, but basically work through that problem, and then we'll take a look at it, and I'll help you with any questions that you have along the way. So as far as our vodcast goes, I'm going to turn it off right now, and this will be the end of the part that will be on this vodcast, so that when we come back, if we're discussing this, we may have another vodcast. And if not, we'll just start with method of sections. All right? So this is not really a homework problem. This is a practice problem for you guys to do together. All right. Off with the vodcast.